This accelerated schedule is by Andrew Graus. He'll be telling us about predictions for gravitational lensing studies.
Thank you. That talk is actually, still the mic.
Microphone. Oh, sorry.
It's fine, I'm loud enough, so. No, you won't be recorded. Okay, fine. All right, so that talk was so nice, I'm going to give a very similar talk. Here we go. Thank you. Thanks, man. All right. So basically, I'm Andrew Graus. I'm a graduate student at UC Irvine, and I'm here to tell you a little bit about the effect of baryonic physics on substructure lensing. So I, like a lot of people here, study galaxy formation. That's kind of the theme of this conference. However, I don't really care about the galaxies that do form. I care about the galaxies that don't form. What I mean specifically by that is most galaxy formation theories include some, critical halo mass limit below which you will not get a galaxy. And this is possibly because of reionization physics or feedback or something like that. A recent illustration of this is these plots from the Apostle simulation. What's plotted here is these are a suite of Milky Way and Andromeda-like simulations and their substructure. The blue points are centrals. The red points are subhalos. But it's not all of the subhalos. This is the stellar mass, but there's a bunch of things that don't have anything in them. And so the fraction of the subhalos that are dark is given by this red line. And so you can see at Vmax is around 25. Everything has a galaxy. Great. But once you get just a little bit lower, down to Vmax is about 10, almost nothing has a galaxy in it. It's 100% dark fraction. So there should be a lot of these dark subhalos flying around. And you could say to yourself, well, that's great, but how do we actually see those things? Well, there are several methods where we can measure this. One I'm going to focus on, just like in the previous talk, is substructure lensing. So I'm going to give a simpler overview of what this is. Here's your cartoon of galaxy-galaxy lensing. You have some foreground galaxy. This is normally an elliptical. And then you have a background galaxy. And what we see when we observe this system is something like this, where there's a ring structure with multiple images and knots given by the specific orientation of the galaxies with respect to us. So this is great, but this is very simple, right? This foreground galaxy is just a smooth elliptical. What happens, but we know the real universe is more complicated than that, right? There's substructure there, some of which has galaxies in them, but some, if galaxy formation theories are right, should be completely dark, right? So what can we do? Well, we can model the things we can see, right? And maybe you get something like this. And then you can take that model, subtract it from the actual data, and you get a residual. This residual is mostly consistent with 0. But if you're lucky, and in 2012 they kind of were, you're going to get something that is significant, a detection of something. And you get a mass out of the models of what this is. So this was the first detection of something of around dwarfish mass scale. There have been other systems that have been looked at, and most of these have resulted in non-detections. However, recently, there was another result from Zave et al. 2016, where they looked with ALMA at an elliptical galaxy at redshift of about 0.3, and they found another detection at a subhalo mass of about 10 to the 9. So what this is a projected differential mass function of substructure, given that the fact that they saw something at 10 to the 9 and did not see anything below that. These are upper limits. So, this is great. So consistent with this emerging field, we've also gotten pretty good at simulating galaxies that form, right? So we've already seen some pretty great hydro simulations. But specifically, we're getting good at simulating very big galaxies, things at the Milky Way scale and even more massive. The bias is towards the Milky Way scale because we live in the Milky Way. But what we've noticed is something kind of strange. So this is this is a recent result from an Arapo simulation of a Milky Way-like galaxy. And what you can see here, this is run with both dark matter only and hydro. And what this is the cumulative subhalo mass function. The black is the dark matter only, and the red is with baryons. And so what this kind of illustrates is that the baryons matter. And normally when people say the baryons matter, they're talking about too big to fail or core cusp. But I actually mean in the literal existence of substructure. So what's kind of been noticed is there seems to be this effect where the potential of the galaxy itself is destroying substructure. And this is about a factor of 2 effect, which is actually kind of a big deal. So I, like Feng Zhao think that simulations are very hard to run. So, but I think that we need baryonic simulations to kind of interpret these lensing signals. So much like Feng Zhao, I think simulations are hard to run, so I didn't run my own simulation. I used the Illustrious. So this is publicly available, and this is great. I need this because it was run both in dark matter and full hydro. And so what I did was I went into the publicly available data catalogs and grabbed the redshift 0.2 snapshot. This is about the average redshift of these lensing systems. And then grabbed all the halos that were kind of above the Milky Way mass scale, right? So somewhere in the a few times 10 to the 12 to a few times 10 to the 13 halo mass. So when I do this, the first thing I can do is just plot a cumulative halo mass or cumulative subhalo mass function. So this is everything within 300 kiloparsecs of each of those systems. And what you can see is an effect similar to what I showed from that Repo simulation of the Milky Way, right? But this is at much higher mass scale. The baryonic or the dark matter only simulation is black, and the baryonic simulation, the full hydro run, is magenta, and this is a residual, so it's about a factor of 2 effect at all of these subhalo masses. So it gets a little bit weirder. So to compare to lensing, I can do this projected differential mass function thing. And when I do this, this is what I get for the dark matter only run. So you can see it lies a little bit below the Hazave et al. Point, at the point where you might think this is a little strange. Another thing to point out is this is in a projected radius of 40 kiloparsecs, which is actually a fairly bit larger area than is probed by these lensing surveys. Now, as you might anticipate, if I look at the baryonic simulation, things will get worse. And so this is odd. I don't necessarily know how to explain this. But what I do think is very important to note is it could be a mass definition issue. So the masses often quoted in these, the masses that come out of these substructure lensing things are often based on an assumed pseudo-Jaffe profile, where the masses they give, the subhalo masses they give, are the mass within some tidal radius. And this tidal radius is dependent on the Einstein radius of the lens itself. And so it's not necessarily easy to correlate that between a halo mass spit out by a halo finder, right? And so, in addition, anybody who's worked with halo finders has noticed that they don't necessarily even give consistent results with each other. Whoops. So one thing, so this is what I basically did to kind of show this is went into Illustrious, grabbed the particles from the systems I'm interested in, and ran a couple of halo finders on them. And what you see when you look at the halo masses is that they're kind of different. So this is from the baryonic run, and what you see is subfind is this magenta line, Rockstar is this gold line, and AHF is this green line. And this is kind of an interesting offset. So you might ask, okay, well, is there a consistent parameter we can use? I actually think so. I think it's the subhalo Vmax. So if I switch to Vmax, now this effect is much, a little bit alleviated, right? There's still a little bit of contention here, but I think it's still, I think it's a pretty decent agreement. So now this is kind of, I'm at the end. I'm going to end with some takeaways. So I think substructure lensing is a powerful method for detecting possible substructure. But I think we need accurate predictions from simulations with full hydrodynamics. The important thing is the full hydrodynamics in order to interpret these results. So I'm not the only one doing this, as we just saw in the previous talk. Also, I'd like you to point you to a recent paper by Fiacconi et al., 2016, who saw a different result than I'm seeing, but I don't necessarily think it's inconsistent, and I think that's important. But I also think we need a consistent measurement of halo properties. We kind of need to talk to these substructure lensers and come up with a good metric for how to measure these systems. That's it. Thank you for listening.
Since the result in Fiacconi Dow et al. Is essentially the opposite of your result, why do you think there's no contradiction?
So I'm not. So me and David talked extensively yesterday, and we are not convinced that it's necessarily the opposite result. There are a couple things to keep in mind. So this is the Fiacconi result. I think the main thing that I want to stress with my talk is that that the baryons cause a significant difference, right? And so they also see this as well. If you look at their, basically for those of you that don't know, the Fiacconi result was based on simulation of a elliptical-like galaxy, both in hydro and not. The hydro is this red block, and the non-hydro is this black block. And you can see there's a little bit of a suppression in substructure in the hydro one, which is mainly what I wanted to point out. As far as why they're actually consistent with the Hazave et al. Result, I think a lot of this has to do with exactly how you're orienting your line of sight. So I just chose a random line of sight, but a lot of these lensing systems, you're looking down the most dense axis. So what I'm in the process of doing is looking at, well, if you just are looking at the most dense axis in all of these systems, does that change your result? And I think it will significantly.
So I didn't quite understand how mass definitions would reconcile the result, because when I look at your plots, particularly a comparison with hydro simulation, there is more than an order of magnitude difference. And so you would need to have mass definition errors or mismatches to be order of magnitude. It's hard to believe that.
So I think you're talking about the offset between the dark matter only and the baryonic.
No, between the data and baryonic prediction.
Oh, okay. Yeah, so I think that's the problem. Like, this again has to relate with how you're orienting your line of sight, right? If we're looking at the most dense axis, this line would presumably move up, but I'm not necessarily sure it'll save you once you include the baryonic physics.
Isn't line of sight in your scatter that you show?
The scatter is from all of the systems from Illustris. There are about 700 systems.
That's effectively line of sight variation also, right? Because you're observing them randomly.
Yeah, I mean, it may be. But if they're all, these lensing systems are preferably viewed down their most dense axis, we believe.
Okay, I'll get over there. Sorry. Edmund, you didn't. You're just stretching. Stretching is good.
So, so in the hydro round, the subhalo mass function is a factor of 2 lower than the dark matter only round, which makes the tension worse. I want to say that another thing could save this. That is, when I calibrated my model to simulations, I find that there is very strong subhalo disruption existing in simulations. Basically, about 50% of all the subhalos ever accreted by the host halo for some reason disappear in the evolution. This doesn't necessarily happen to low mass subhalos. This occurs for subhalos of all masses and at all different halocentric radii. And this would boost the subhalo mass function by a factor of 2, which compensates for the hydro decrease.
That seems cool. I don't know. Maybe we talk about it a bit later.
Okay, last question. Sure.
Yeah, just a comment. So a brief comment on our results. So
yeah,
one thing that is important, that we find important, first of all, is the kind of halo that you're looking at. So we were looking at more massive halos that assemble later, right?
Yes.
And even the assembly history of those halos itself, as Yang showed, I mean, there is a big scattering. And for the halo that assembles later, so it's slightly less viralized than the other, then you can see in the projected mass fraction of subhalos a very big scattering given by the line of sight, and even a systematic difference between the two subhalos, given the fact that the one that assembles a bit later lies above the other halo. So there is also this to be taken into account.
Right.
Okay, thank you.